Examples of the non-Newtonian fluid is such as chili sauce or tomato sauce. If you go to the McDonald's, if the restaurant does not provide you with the packet sauce, they will give you a sauce in the bottles. So if you want to have the sauce come out from the bottle, you have to shake it first, and then it allowed you to allow the sauce to flow easily, right, to the plate. But for air, it does not need to have when after you take off the cover, it will flow down easily compared to the non-fluid. Now we're going to look at the variation of the dynamic viscosity with other property such as temperature and air pressure. We're going to look at the air, right? Air and water, because air and water will be uh, the most used fluid in this our course. So we can see the parameter there consists of a pressure, right? The parameter of this graph is pressure, and then we have the vertical axis is dynamic viscosity, and the horizontal axis is the temperature, which varies from minus 200 degrees Celsius up to 1600 degrees Celsius. It's very interesting to see the behavior of fluid with the increasing pressure and temperature, right? Or at constant value of pressure and temperature. And the unit for pressure is 1 bar, right? In the plot. So 1 bar is equal to 1 times 10 to the power 5 Newton meter square, or you can use Pascal. 1 Pascal equal to 1 Newton per meter square. And then we also interested to see what happened to the viscosity at high temperature. When at high temperature, the viscosity is increasing when the pressure is become lower, right? So yeah, I think the plot is should be decreasing pressure and increasing temperature. So when the uh, at high temperature, the viscosity of the fluid is increasing when the pressure is lower. And at constant temperature, we can see that at 1 bar, the, the viscosity is become lower as the temperature is increasing. And the application of viscosity at high temperature can be seen in the combustion chamber, right? Now we look at the variation of the air properties on tabulated data, right? So you can also obtain the values of the dynamic viscosity from appendix of the books or from the field property data. Right, from this graph, you can see that at the room temperature between 20 to 30 degree, the kinematic viscosity is about 1.56 times 10 to the power minus 5 meters square per second. Meters square per second will be the unit of kinematic viscosity, and dynamic viscosity for air is about 1.8 times 10 to the minus 5. And you can also see that the density of air at 25 degree about 1.18 kilogram per meter cube. Next, we look at the density dynamic viscosity of water and its relationship with the pressure and temperature. Again, the plot, we have relative velocity with the pressure, and our parameter now is the temperature. So we find that the viscosity is increasing uh, when pressure is increasing and temperature is we have the decreasing temperature, right? And then we have increasing pressure to the right. So at high temperature, density of dynamic viscosity of air um, is increasing. Um, when the temperature is lower, the dynamic viscosity is increasing. So in our course, we will assume that as part of the initial assumption that the dynamic viscosity is constant or constant property fluids, right? As our engineering assumption. And then we look at the tabulated data for this dynamic viscosity of water. Right. From what we see that the dynamic viscosity, kinematic viscosity of water at atmospheric pressure at room temperature about 20 degree is about 1.002 times 10 to power of minus 3, right? I think 3. Oh, sorry. The way that we're going to read this table is quite we have to be very careful when reading this table because the actual values of kinematic viscosity will be 1.002 times 10 to minus of 5. So when we look at the heading, is 10 to power of 4. Sorry. So we have to multiply what we have here with 1.002 times 10 to minus of 5 times 10 to 4, that will give us the value of kinematic